Well, hello everyone. My name is Jake, and today we're going to be learning the basics of Git. I remember when I first learned Git, it seemed like a really daunting task. But after it clicked, it became an invaluable tool when writing code. So my goal by the end of this is that if you don't use Git, you don't know how Git works, you'll start using it and you'll understand it. If you don't know how to use Git, I want to strongly encourage you to listen to this talk closely because this tool will save your butt more often than not. And because of that, it's pretty standard in industry, and you'll be using it a lot. So also, I hope to make this talk into a series of talks, with each presentation diving into a deeper part of Git, which is why you see the part 1 there. All right, so first, I want to introduce a scenario to you. Okay, so you're back in CS1. For some of you, that's closer than others. For some of you, that's really closer than others. And you've been given an assignment where you have to write a Python script that does all the basic math operations. We're talking addition, subtraction, division, multiplication. I know, really, really difficult stuff. So I have, let me just mirror here. Oh, that's going to be an issue. All right, can everyone see that? Good. All right, so I have Kali open. Let's make a very simple program, and it's going to take in an argument, or it's going to take in 2 arguments. And then we're going to do a mathematical operation on it. Just riveting stuff. I know, it's risky. All right, so we're just going to print, all right, we want to do some addition. And we're just going to print arg1 plus arg2. All right, dope. Let's see if this runs. Oh, I'm going to need arguments. All right. So that's an issue. That was all part of the plan. All part of the plan. All right, hey! So we're happy with this, right? It does what we needed to do. We decide, you know what? Let's clean up this code, and let's make a function out of it because we're good programmers. And we're gonna functionize this riveting functionality. It's gonna take in 2 numbers, and it's gonna return the sum of them. All right. Now this one's gonna be on purpose. Let's convert this, use our new function, add all the parentheses, and, let's see here. Oh, duh. Wrong name. Hey. All right, so, well, this one was on purpose. Yeah, so this frustrates us, right? We just had it working. We didn't really change any logic, even though we did. We didn't think we did. And there's no way to get our code back, right? Obviously, this is a simple example where it's easy to see what happened. But as you have a larger code base and a larger file, when you change stuff around, you're going to run into issues where, well, now I don't have the previous version to revert back to. So we fix our issue. And let's just fix it up here. Run it again. All right, we're all good again. So we decide, you know what? I know what I'm going to do. This is something I did. I'm going to make a copy of this file so that if I need to revert back, no problem, right? I just copy that file. I just go to the copy. So we're going to make a copy, make a backup file, and now we're good, right? Now we can edit this file and revert back. But the question becomes, that's annoying. That doesn't. You got to switch back like that. Oh.
Very nice. Like the background.
Come on. Here we go. There we go. So the question is that solution practical? Or making backups of files? Think about, what if we had 1,000 files in our repository, right? That would be insane. Last time I looked, which was a few days ago, the Linux kernel project in GitHub has around 65,000 files. If we're making backups of all those files, quickly it's going to become money. We're not going to know what to do. So wouldn't it be nice if we had a way to track these files without having to save different versions of the same file? Well, we do. It's called version control. So version control is a system that records changes to a file or a set of files over time so that you can access specific versions later. Also, you don't lose the things. There's many benefits. As we just discussed, it cleans up your file tree immensely. It gives you the ability to revert back. It tracks who changed what and at what time. That's nice for big development teams when a developer pushes up a code change that breaks things. They want to know what happened and who did it so they can fix it. And you can recover data if it's corrupted or lost. And as a side note, version control has a very low overhead, or at least Git does. So we get all of this functionality at very low cost. So okay, Jake, I'm sold on version control, right? We're past CS1. What are the different kinds of version control? Well, I'm glad you asked. The first and most basic of version control is called local version control. Local version control systems works by having a local database that tracks all the changes related to a desired files. If you've ever heard of RCS, revision control system, that's an example of this. This is an old Unix version control utility. So to illustrate how they work, I busted out some PowerPoint animations. And if we think back to our math.ops, when we added, say, if we want to add subtraction, maybe we save that as another version. We want to add division, we'll save that as a third version. And now we can revert back to old versions if necessary, right? If we break something, if we have an issue like that. So local version control is pretty sweet, right? Well, it's got one glaring issue, which is collaboration. How would developers collaborate with others on the same project? Would you send the database every time you made a version change to another developer, right? That would be unwieldy and not sustainable. So to fix this, developers started using centralized version control systems, which work by having a single server hold the version control database for every file we're tracking. So developers download the specific version of code they want, and this approach allows developers to collaborate more easily on the same project, right? They don't have to send it back and forth. They're all pulling from the same source. If you ever heard of CVS or Subversion, that's an example of centralized version control systems. So okay, now we're sold on centralized version control systems. We can collaborate. They're the way to go, right? No issues? Well, there's actually still one issue, which is there's a single point of failure. What if the server is down for maintenance? What if the server becomes corrupted and there's no backup? The developer only downloads that one specific version they're working on, which means the version control database or the list of versions is still stored in the server. So to solve this, developers switch yet again to distributed version control systems. So they add the ability for every developer to download the entire version control database with the version of code they want to work on. Now if the server goes down, any client can restore it because it mirrors exactly what was stored on the server. If you've heard of Mercurial, this is an example of distributed version control systems. And, drumroll please, another one, Git. Sorry, I should. So as a quick history lesson for all you trivia nerds, Git was created to manage the Linux kernel project. From 1991 to 2002, they were managing it by passing around patches and archive files. In 2002, they decided that this was not a good approach. So instead, they're going to use a distributed version control system called bitkeeper. And then in 2005, bitkeeper decided that, you know what, we're not going to be free anymore. And the Linux community, and in particular Linus Torvalds, developed Git. Git is a distributed version control system. At a high level, Git works by taking snapshots instead of tracking file differences, as is typical in most version control systems. That's called delta-based version control, which is, here's an example of that. Git thinks of data more like a series of snapshots of a miniature file system. After every version is saved, Git takes a picture of what all your files look like at the moment and stores a reference to that snapshot. For efficiency, Git stores a link to unchanged files instead of storing them more than once. So before continuing on with how Git works, first we need to take a quick look at some basic terminology. First, a repository refers to a directory or folder containing your code. When you create a Git repository, Git will actually create a .git folder, a hidden folder in your directory, which will act like a local database and way to track your code. The verb checkout is used to refer to loading a desired version of that repository. And then finally, to commit means to save the current snapshot of files into a local database. Okay, now back to how Git works. Git has three main states that file can reside in. First, the modified state refers to files that have been changed but not committed. Second, files in the stage state are ones that have been marked to include in your next commit. And then finally, the committed state refers to files that are safely stored in your local database. So armed with this, let's look at an example of a Git workflow and how files transition between the states. Okay. So I first start by grabbing a specific version of the files and putting them in our working directory. Next, I may modify some files, make some changes, add some division code, yada yada. After this, I selectively stage only the changes we want to include in our next commit. And then finally, I do a commit, which takes the files in the staging area and stores a snapshot permanently to your .git directory. So, okay, Jake, I understand high level Git. How do I get it set up on my computer? Well, the long and short of it is either use a package manager or download an installer. I won't go over that too much. You can look that up. Something I will say, though, is that after you download it, you should do some configuration for Git, which includes adding your username and email, which will be used when you make commits. It'll tag who made this commit and how you can contact them. And then you're going to want to set the core editor you want to use. So if you're not a fan of Vim or you're not a fan of whatever, you can set that there, which may be useful later. To see all your current configuration settings and where they're set, you can use the git tag list, tag show, tag origin command, and that's going to show you all the commands you have, or all the settings you've made and where you set them, because you could set them in different areas to affect different parts of your repository if you have a lot of nested folders and whatnot. All right, so now it's time to learn some basic commands so we can turn our math operations code into a Git repository. So first, to initialize a Git repository, we use the git init command. This is going to create that .git folder we mentioned earlier. And then once I've done this, I'm going to want to add some files to the staging area so that I can commit them. We do this by using the git add command. Fun fact, you can specify files in the git add command with wildcards, absolute paths, or relative paths. So it's pretty flexible. And then after we've added it to the staging area, as we just talked about earlier, we're going to we can commit a file using the git commit tacm command. If you don't use tacm, you're going to get a pop-up from your default editor and where you can add a commit message. Tacm is just an easy way to add a commit message right on the command line. Then finally, if you ever want to check what files are in what state, use the git status command. And if you want a short output of that, use tacS. So with this in mind, let's add our math ops code to a Git repository. Ooh. Let me go back to, I want to do this. Come on. Duplicate. All right, we're up and going. Okay, so let's start by initializing our repository. And we see we get a message back from Git saying your repository has been initialized in this directory. And we see that .git folder on the end of the directory. If we list our hidden files, we can see the .git directory right there. Also, real quick, I have written a little bash script to enter those config commands. As we see here, I'm going to run that so that we could see all our settings there and whatnot. So as you see at the top, I have my name, email, editor set. The stuff at the bottom was set by that git init command. So now that we have a repository initialized, let's check the status. And we see that we have a directory and these 2 files that are, it's saying untracked. So if we go back to our example here, we see that next thing we need to do is we're going to add the file to the staging area to make it a tracked file. So to do that, we're going to do a git add, if I could type. Now we could specify this file specifically. We could specify all files that end in .py. We could do a complete path, or we could just add every file, which is what I'm going to do. And then if we do a git status again, we see now we have these 4 files that we're tracking. I just realized I don't want to do the .pk file. So if we look at under the message that says changes to be committed, we can use the git remove tech.cached to not remove that file entirely, but make it untracked. English is hard. All right, so now we check the status again, and there we go. We have we've added the files we want to the staging area, and now that we have the files we want in the staging area, we're ready to commit those files. The commit's going to take them from the staging area to it's going to make them in the unmodified committed state. So if we do our git commit tacm initial commit, you'll see this a lot. It's pretty standard. And there we go. We get this message back from Git saying we have 3 files with 19 insertions total, and it lists the files, gives us some stats on that. So if we check the status again, we see that, and actually let's remove that file because we're not doing that anymore. We see we're on branch master, which we'll talk about later, and there's nothing to commit. Our working tree is clean, right? Every file is in that unmodified committed state. So now we have some options with our files. We could either edit the file, which is going to take it to the modified state, or we could remove it completely and take it to the untracked state. I'm going to edit it. Let's add some subtraction functionality. And then we're going to print it out. Oh, I made that mistake last time. See, I learned. And we're going to test it. And there we go. All right, so we're pretty happy with this. We got some subtraction stuff going. So because we're happy with it, we were going to stage the file to commit. So we want to save this functionality so that we don't lose it later, and we can revert back to it if we need to. So we're going to add the file again. We're going to check the status to make sure it got added. We see that we have 1 file ready to be committed, and it's modified. And then we're going to commit. Commit messages generally, they want messages to read more like add this functionality, not added this functionality, because when people look at commits, they want to see what exactly changed from one to the other. So we're going to say subtraction, and then we get our message back, 1 file change, 4 insertions. Check the status, and we see that all the files are now back in the unmodified state. So Let's change this back to extend. So I get my notes back. All right, so now we have a few commits that we've looked at. Wouldn't it be nice to have a way to see a log of all our past commits? Well, we have one, Git Log. I'm not going to go too into detail about this command, but I encourage you to look at the man pages and the other resources I list at the end of the talk. There's a lot of options for Git Log. A lot of them are very nice for displaying your data in specific ways. You can actually format your data to say how you want to display. But let's try out these commands and see what it shows. Man, this is annoying. Duplicate. All right. So if we just do a simple git log command, we see that we're given a log of all our commits. At the top, you're going to see a long string of what looks like gobbledygook. That's a hash. That's going to represent your commit. And with every commit, we see our config data, our name, and our email, and then a timestamp as to when that happened. And also with our commit message. So, but that's a lot of data. So if we want to look at something a little shorter, we can enter that command, and now all we get is the commit ID and the commit message. But if we want to, we can also specify a specific way to format the data. So if the pre-baked ways aren't good enough, we can make it do whatever we want. And this one, you see a short hash. Let me do this. You see a short hash, my name, how long ago it happened, and the commit message. So a lot of functionality with Git commit or Git log. I definitely I recommend you look into it. Okay. So now we know how to track our code, right? We got the basics down. And honestly, just that is going to help you out a lot. You're not going to lose data. You're going to be able to revert back when we learn about that. But what if two developers want to work on their own copy of the same repository so that the one developer's code doesn't affect the other, right? Or what if we want to keep different versions of the same repositories which represent varying levels of stability? Like maybe a develop section, this works section. Or do we have to copy repositories and keep separate repositories? No, that would be ridiculous. So have no fear. Allow me to introduce Git Branching. By default, a branch named master will be created in every repository when issuing the git init command. And I think the best way to learn Git Branching is by giving an example or where it is helpful for doing it. So first, the example. Let's say you're a developer and you received a feature request for your code, right? You've made a few commits first on your repository, and you receive this feature request. You don't want to make any changes to the main master branch because you want that to represent all your stable code. So midway through, so what you do is you're going to create a branch. This branch does not affect the master branch. It's going to be its own separate, think of it almost like its own separate copy. It's not exactly how it works, but that's okay. So midway through working on this feature, you get a call from the boss saying, hey, we got another fix that's critical. We need to implement that. We need to get that stuff figured out now. So we don't want to lose our work in our feature one request, but we also don't want to touch master. So to do this, we just create a third branch. This is going to be the critical fix. And so we can make some commits, and now we have all our code with that fix in a separate section, a separate branch. And Git branching enables us to come back down to our first feature once we're done and keep working on it. It is extremely helpful. And under the hood, it doesn't actually make copies. It changes pointers around. But that's okay. We don't need to talk about that yet. So now let's implement this in our code. And let's check. Let's make sure things don't get changed from one branch to another. So to check which branch we're on, we issued the git branch command. Later, we'll see more than just master here. And the asterisk at the left specifies what branch you're currently on right now. So to create a branch, we're going to, let's call it feature 1, like we had in our example, and issue the git branch command again. And we see that we have feature 1, but we're not on feature 1 yet. To get on feature 1 and start using that branch, we're going to issue the git checkout command. And we get a message saying we switched. And if we check that, now we're on the feature 1 command. So if we go back into our code, right, and let's say we want to add some division code. Return num1, num2. Okay, let's check this. And awesome, works. We got it working. So because of that, we're going to use our trusty git add command, add this code, and then we're going to commit it. Add division. Ooh, forgot my flag. And we see we have our everything works out like we wanted it to. So now though, if we change our branch to master, check that we're on master, and we look at this code, we notice that we don't have the division code in there, which proves that we can, on different branches, they're not going to affect code on other branches, which is nice. So in our example, we created a third branch. We could do it easily the same way we did it here. Let's see if this will work. Oh. Ah. And there you have it. That's the basics of Git right there. Last thing I want to talk about before I leave is the difference between Git and GitHub, because you'll hear about both. Git is that distributed version control system, as I mentioned, and GitHub is a cloud-based hosting service that lets you manage Git repositories. Think of it like a front end for Git. Just a quick primer on that. And then lastly, I want to make sure to shout out the book Pro Git. It's actually a free book. It's like 500 pages written by 2 developers on how Git works, the inner workings of Git, how Git manages in your files. It's really nice, and it's where I got a lot of the content for this. A lot of diagrams came from that book. And then also I listed a few YouTube videos that I thought would be helpful for someone learning Git. Any questions? Good?